Meeting is being recorded.
Okay, you tell me when I should go ahead and start.
Yeah, that's good. Okay, everybody, today we have Prof. Romatschke from University of Vienna here to give us a talk about negative coupling field theory. Thanks so much for waiting. Please go ahead.
Oh, okay, no worries. Yeah, thank you for having me. My kids complained when I told them this morning that I was going to Japan, and they said that I absolutely have to bring back sushi. And I said that that would be difficult, but maybe next time. So today I want to tell you a little bit about my group's endeavors into the field of negative coupling field theory. And since this is a very recent sort of development, I will sort of try to take you slowly into this sort of uncharted waters by first telling you about how we sort of got there, and then maybe give you some physical handles on what negative coupling field theory is and what it can do for you. The structure of the talk is very much such that I would welcome you to sort of interrupt me with questions if you have them. So please, at any time, just unmute yourself, ask a question. I'll try to sort of answer them as much as possible. I don't have an agenda. I don't have to go through all my slides. So we can sort of go to slide 10 and have a productive discussion. That probably would be preferable than sort of me going through this in a fast fashion. Okay, without further ado, I want to talk about negative coupling field theory. For those of you who have not visited Vienna, this is basically where we are. This is TU Wien. I don't know, can you see my mouse here or not?
Yes.
Okay, very good. Yeah, so this is the old building of TU Wien. I'm actually in a sort of slightly less fancy building, but higher up. So this is where I'm talking to you from, and what I'm talking to you about is field theory. So from a very high-level perspective, field theory is defined as a path integral with an action of the theory, classical action of the theory, in Euclidean space, which I've written down here. So it's an integral of a space, and then you have a kinetic term and a potential term. The textbook case is that you set up quantum field theory for potential V that is both real and bounded. So for instance, a potential V of phi that is just m squared phi squared plus lambda phi 4, where the coefficient of the highest power, so the coefficient lambda for the phi to the 4 term, is real and positive. And there are good reasons for doing that, because if you have such a potential, it has a shape that is, for instance, depicted in this graph here. It's a potential of the form of a valley. And in classical physics, valley potentials are nice. They sort of have stable ground states. We sort of understand what they do. So that's a good way to sort of, if you want to build up your quantum perturbation theory, so perturbation theory in the H-bar, and that's basically what is usually used in textbook quantum field theories. Just to show you, if you sort of have in classical physics a ball that you place into its potential, you can characterize the energy of the ball simply by essentially either its potential energy or its kinetic energy, or if it's moving by the sum of both of them, and it will just be somewhere inside this potential. Of course, we know that classical physics is not the whole story. There is a long development that tells us that quantum mechanics sort of is the actual sort of true description of these sort of physics, and we can ask ourselves how quantum mechanics would modify this classical intuition of a ball or some sort of ground states in such a potential. And the answer is, of course, very much a textbook case. We have to sort of quantize the theory by sort of putting boundary conditions. And even though for many potentials we don't know the spectrum, these energy spectrum, En, analytically, we can nevertheless always find them numerically, for instance. And for the potential that I showed you before, this phi to the 4 potential, the energy spectrum is characterized here in terms of these lines here. So you have the ground state energy, which is not zero, but some finite value. Then you have here the first excited state, second excited state, and so on and so forth. So this is a textbook case. All of you have sort of done some version of this in your undergraduates. So I will not go into the details of this because otherwise you will bring back memory of your sort of tests in quantum mechanics. So what I really want to use this for is a ramp into the field of negative coupling field theory. What do I mean by this? I mean that you start out with the same setup. You write down a Euclidean action for the theory that is the same formally as the one that I had before. But now you consider a case where the coefficient of the highest power term, in this case the phi to the 4 term, is negative. And it's customary, instead of writing it as lambda with lambda negative, to write it as minus g and take g to be positive, right? So g is not a negative coupling constant if it's positive, and the potential sort of takes this form. So if you do this, and if you consider this case, then classically, you immediately see that you have a problem. This is the form of the potential for some positive g. So this is the negative coupling field theory in classical physics. And as you can immediately see, from a classical perspective, this potential does not have a stable ground state. You can sort of, again, go through this exercise where you put a ball on this potential here, initially addressed. And then you ask what is the energy of the ball. And sometimes I sort of ask my student that as a test question. But for you, I will immediately sort of solve the test question by telling you that in classical physics, the energy of the ball is infinite, because even if you put it at this potential addressed, then the fact that the potential does not have a classical ending means that it has infinite potential energy, so the total energy of the ball is infinite. So because of this, there is this statement that these upside down or endless Hill potentials make no sense in classical physics. This is easy to understand. They don't have any classical ground states. We usually dismiss them as sort of nonsensical from this perspective. However, I told you before that sometimes quantum mechanics can have interesting results that do not often conform to classical intuition. And I will sort of prime you by telling you that I'm sure that all of you know at least one classically unstable system that is well defined in quantum mechanics. Can you think of which one I'm having in mind? Any suggestion?
Stable, it could be the free particle. I mean, it does not have a stable minimum, but you can sort of solve it.
Yeah, no, I think now I'm having a sort of much more sort of. So if you think of a classical problem that would tell you that, okay, this system does not have a stable ground state, but then you go like, oh, but quantum mechanically makes sense. Only if you have solved this problem in undergraduate physics. I give you a hint. It has something to do with electromagnetism.
Hydrogen atom?
Yeah, there you go, the hydrogen atom. Okay, hydrogen atom has a potential that is sort of shown here in terms of this red line here. So the sort of potential of the core is minus 1 over r, and that potential sort of is depicted here. It doesn't have a sort of well, it goes to minus infinity at r is 0, so at the core. And we know this from classical physics, right? If you take a charged particle, an electron, and you put it on a circular line because it's radiating, it would basically lose energy and would crash into the core. So this is why people, before essentially the event of quantum mechanics, thought that this could not potentially be a stable system, because classically a rotating charge would basically spiral into the nucleus, and that could not be the structure of the hydrogen atom. And it was really sort of the triumph of quantum mechanics to realize that no, if you treat this problem quantum mechanically, you find that this system does have a quantum mechanically stable ground state. It's this famous minus 13 point something eV. Okay, and then you have the first excited state, second excited states, and so on and so forth. Okay, so this is a system that does not have a classically stable ground state, but quantum mechanically is perfectly well defined. Okay? And there's, I think, no more discussion about the hydrogen atom in the physics community. So what I want to sort of do now is tell you that, okay, if we take this as an example of something that works in quantum mechanics and does not work in classical physics, maybe we should just, instead of dismissing potentials that are classically unstable, maybe we should actually first calculate and see whether this system has sort of quantum mechanically nice properties, rather than dismissing all systems that do not have classically well-defined properties. So specifically, I want to talk about what happens if you consider this upside-down quartic potential, V of phi is minus g phi to the 4, in quantum mechanics, and see what the spectrum of the Hamiltonian is. Okay, maybe let's do this. So, what do you think is the spectrum of a Hamiltonian with such a potential? Any suggestions?
Depends on the boundary conditions.
The boundary conditions are the usual, so basically it has to be such that it's normalizable wave functions at infinity.
But if you had a mass term, there would be some bound states I can think of, but beyond that.
Yes, that's right. You're very close already. So there's sort of, if you have not sort of treated this problem, there's sort of the naive thing you can think about is if you do this not with a quartic potential, but with a quadratic potential, right? So instead of having a harmonic oscillator, you take the inverted harmonic oscillator. And then it's easy to do because you know what the energy spectrum of the harmonic oscillator is, right? The energy spectrum is just omega over 2 times n. And or n plus 1. And then what happens is that if you flip the sign from omega squared to minus omega squared, you get the energy spectrum to be purely imaginary. Okay, so it becomes I omega times something. Okay, so this is what happens for the quadratic potential. So this is a potential sort of answer to this problem. However, the issue is that the form of the spectrum crucially not only depends on whether it's upside down, but also on the power that you have over here. So let me show you what happens for this particular potential, the minus g phi to the 4 potential. And I will sort of emphasize that I'm not doing any sort of classical physics. I'm really sort of treating this problem quantum mechanically. There's a very nice paper by Jones and Matteo, who were able to prove that this upside-down quartic potential, the minus x to the 4 potential, is isospectral to a potential that's listed over here, namely plus 4gx4 minus square root of 2g times x. It's a beautiful paper in mathematical physics. I sort of, again, encourage you to sort of maybe look this up and go through it. I really sort of enjoy giving this paper as kind of like a test problem in my quantum mechanics course for graduate students, because it blows their minds that this is possible. But the main upshot of this is that if something is isospectral, meaning that it has the same spectrum of both of the theories, and here we have this upside-down potential, and over here we have a potential that is perfectly fine, so it's bounded on the boundaries. The highest power, x to the 4, is positive, but it has a term that breaks parity. Okay, so this is what comes out of the calculation. You get this sort of funny lopsided potential, but you can show that the spectrum of the Hamiltonian of these two potentials is identical. Here it is. It's shown in this plot that was actually sort of known numerically 10 years before the paper by Jones and Matteo. This is Carl Bender and Stephen Böttcher's famous paper from 1997. It's called PT Symmetric Quantum Mechanics. And what they did back then was to numerically study the energy levels of Hamiltonians that are a slightly larger class. So they are written down in this caption over here. They studied Hamiltonians that were momentum squared minus ix to the power n, where n need not necessarily be an integer. So for the case at hand, if you take n is 4 here, you get precisely this minus x to the 4, and you can sort of see the ground state energy from this plot here being somewhere around 1.5, first excited state around 5, second excited state around 12, and so on and so forth. And they sort of did this numerically for all of these different Hamiltonians that I should emphasize, because of the I in there, these Hamiltonians are not even Hermitian. Nevertheless, the spectrum is real, positive, and bounded. Okay, and you can nowadays understand this by realizing that even though the Hamiltonian is not Hermitian, it fulfills a restricted set of symmetries. Namely, it's symmetric under the combined action of parity flip, P, and time reversal flip, T. And this action of this combined PT symmetric action, if you have sort of Hamiltonians that are symmetric under PT, is sufficient to guarantee real and positive eigenspectra. So you can build up quantum mechanics the usual way, meaning that you emphasize that if you have Hamiltonians that are Hermitian, this is a sufficient condition to have real and positive eigenspectra, but it's not necessary. There are weaker conditions that are sufficient. For instance, PT symmetry is a sufficient condition to give you real and positive eigenspectra. And if you have not sort of dealt with this, I should emphasize that this is not something that is, it came out of mathematical physics, but PT symmetric quantum mechanics is a big thing in nonlinear optics. You can build these potentials by having complex media that have complex refractive indices, and you can check these predictions from quantum mechanics, and they sort of nicely sort of describe what's going on. Another system where this PT symmetric quantum mechanic is relevant are open quantum systems, where because you have a gain and loss term, the effective sort of Hamiltonians are non-Hermitian. And also for these systems, you can use PT symmetric quantum mechanics to sort of describe experiment. So again, in quantum optics, PT symmetric quantum mechanics is a well-studied subject. Tens of thousands of papers have come out on this. It's sort of it's mainstream, but for some reason, this message that this is possible has not really arrived in high energy physics yet. So that's basically my main message of this talk. Any questions up to this point?
I'm not sure. Will you explain? So in the previous page, you had two potentials, and then you the work of Jones and Mateo. How did they show this is isospectral? Like,
yeah. So there's a set of mathematical sort of steps that you have to take. Essentially, the way, I mean, in a nutshell, what you do is you sort of start out, then you do essentially sort of rewrite the path integral by sort of introducing something like canonical momenta, and then you sort of switch momenta and space variables, and it, yeah, and the sort of if you want to say the parity breaking term comes from the fact that your measure doesn't transform under this switch between momenta and so yeah, okay, I think I'm not doing a good job in explaining what's going on here. But essentially what they do is they sort of, instead of using a position space representation, the isospectral potential is actually momentum space. So you can think of this as being V of P with 4gp to the 4 minus square root of 2gp. But because in quantum mechanics, momenta and coordinates can be treated on equal footing, the sort of Hamiltonian can be shown to be isospectral. But really, sort of, yeah, it's worthwhile sort of going through the steps. It's not a long paper. It takes you maybe 10-15 minutes to go through the steps and sort of see what the sort of main subject is. I really sort of like giving this problem to my quantum mechanics students. They really sort of chew on it for a bit, but they sort of really, at the end of the day, sort of come back and say that I really learned something by sort of going through this exercise.
So there will be many potential examples of this that you can find isospectral.
Very good question. Yes. So no, unfortunately not. To my knowledge, the x to the 4 is one of the few examples where you can find a Hermitian isospectral Hamiltonian. For most other cases, you only can do the numerical evaluation, and you don't know what the isospectral Hamiltonian is. These are two different sort of things. So this plot here was not generated using an isospectral Hamiltonian, but pure numerics. And I will tell you how to get to the numerics in a moment. Other questions? Okay, then let me proceed. One way to actually sort of do the numerics is via contour deformations. So just to give you a perspective, normally when you write down a path integral, for instance, for quantum mechanics, you have an integral where the integration is over the real line. So think of integral d phi, where phi goes from minus infinity to plus infinity. And this is depicted in this graph here, where I have the real part of phi here on the horizontal axis. That's the normal integration contour. However, because this is a complex integral, you can deform the contour away from the real axis into the complex plane. So this is the complex integration plane. So if you sort of think of an integral dx, instead of integrating from along the real axis, you're now integrating along a complex curve in the complex plane. And one particular set of curves that has been useful is this kind of like kink curves that I've indicated as a blue dot over here. So you can deform the contour so that instead it runs from it runs at a 45-degree angle, hits the origin, and sort of goes back into the at a 45-degree angle in the other direction. So these contour deformations are not really sort of so the main point is that if you sort of treat integrals like that, what you are actually doing is an analytic continuation of your original integral, because you're not keeping the endpoints fixed. Okay, so normally you can deform integration contours if you keep the integration boundaries fixed, but we're doing something a little bit more than that. We're actually sort of changing the integration boundaries into the complex plane. You can show that they are, so for pretty much any integral, there is a range of curves that give the same result. I have not depicted this in this curve here, but it turns out that for these x to the 4 potentials, you have something like a 60-degree opening cone, both to the left and the right, where you can sort of put your contours, and it doesn't matter where you put the contours, you get the same result. But sort of the 45-degree angle is sort of easy to sort of implement because, yeah, for numerics, you want to sort of choose something that's simple. The main point is that if you sort of allow yourself to look at this contour deformed path integral, then suddenly you can treat numerically integrations that are not classically stable. Okay? And you can actually use this to sort of define not only sort of single integrals, but path integrals, for instance, on the lattice, right? So you can write down, for instance, a lattice phi theory with a potential that is negative coupling, so upside down, minus g to the 4, g phi to the 4, and then use your contour deformation to bend it down in these sort of wedges, 45 degrees, such that you get phases of e to the I pi over 4, that's exactly 45 degrees. And then if you take e to the I pi over 4 and take the 4th power, right, that's the phi to the 4 potential, then you get a minus sign from this that exactly undoes the minus sign of the minus g. So then this becomes numerically treatable on your computer. The price that you have to pay is that the kinetic term, which is d mu phi, does not give you a real number, so you get complex actions out of this procedure. So what you end up with is a path integral that is stable, but has a sign problem, right? So the integrand is oscillating quite heavily, but nevertheless, you can sort of treat small lattices by brute force integration, and you can define, for instance, phi-4 theory on the lattice with negative coupling in this fashion. To show you that this actually works, here's an example of the partition function for quantum mechanics, right? So it's a path integral in one dimension. So you have lattice points along your one direction, which has a length of beta. And then you sort of do integrations at each one of these points with this sort of contour deformed line. And you get a result that is shown here in these blue dots here. So this is ln g as a function of beta g to the cubed. Beta, by the way, is the inverse temperature. And you get sort of these blue dots here. And you can compare it to the Hamiltonian spectrum, meaning the spectrum that you get, for instance, from this isospectral construction of Jones and Matteo, and that is sort of depicted in this red line. And what you can see is that there's essentially a perfect match between the numerics from this contour deformed calculation and the isospectral Hamiltonian from this plot. Okay. Any questions on that? I'm not sure if I explained very well what it is that I'm doing here. So if there are questions,
One-dimensional lattice,
this is a one-dimensional lattice, yes. Which is
sorry.
Yeah, which is one of the reasons that you can actually do this, because yeah, so for instance, you have like 10-dimensional integrals which are oscillatory, but that is something you can still treat on like a modern computer with brute force techniques. It gets much harder if, for instance, you treat like a 2-dimensional lattice or a 4-dimensional lattice. There you run out of steam at around 30 lattice points, which is quite coarse.
Any other way other than multicolor simulations one can look at it?
So again, this is an oscillatory integron. It has complex action. You will not be able to treat this using standard Monte Carlo techniques. It has a bad sign problem.
I think, sorry, my question was unclear. I wanted to say, like, any other new, like, instead of putting it on a lattice, like, can we do something in continuum, like perturbation theory or something, to see anything similar?
Yes, you can, and I will show you results for that in a moment. But at this point, I will sort of take a sort of very sort of standard approach, saying, okay, if I can put the theory in a lattice, then I trust it, and if I sort of do some analytic calculation, people write paper is sort of very lenient. You can write many things on paper, and people either believe you or don't believe you. But if you put it on a lattice, then usually sort of people trust you much more. But I will show you some analytic approaches as well.
So for these isospectral potentials, what was there like no general method to finding them? Was it just sort of the first paper, is that like brute force looking at one specific case, or?
So the original paper historically original paper by Bender and Böttcher, 1997, that is brute force numerical techniques with these contour deformations that I just showed you. Just looked at Hamiltonians where they sort of bent down the x variable into the complex plane and did it numerically using Runge-Kutta differential operators, right? You throw it into a Runge-Kutta and out comes the spectrum. The Jones and Matteo paper, this is purely analytical. You sort of just calculate it through. You end up with this potential here, which is, it's positive, and it's well, the thing is that this potential has an x to the 4, so you don't know the energy levels analytically because we don't know them analytically for the quartic oscillator either. But numerically, this is a well-defined Hamiltonian. You can use any method that you want to sort of find the spectrum for that, and it agrees with the numerical sort of method of this contour-deformed paper by Bender and Böttcher. And both of them agree with the path integral method that you sort of can set up. So all of them sort of agree, essentially. Okay, good. So now let me give you one more sort of perspective, which is, in some sense, a little bit of a repetition of what I said before. One way to sort of interpret this is to say that, well, so what, right? You have a Schrödinger equation. H psi is E psi. The Hamiltonian for this is a kinetic term, so minus d squared by dx squared, and minus x to the 4, this sort of upside down potential. Why don't we just go ahead and solve it? Okay. And it turns out you can do this. I show you here the plot of the wave functions for this inverted harmonic oscillator. You can use different sort of techniques to do this. The main point is that, yeah, you get a ground state wave function, psi naught, psi 1, psi 2. Notice two things. One of them is that the wave functions, even though, sorry, I'm going back, even though the problem here is purely real, the wave function solutions are complex. They both have a real and an imaginary part. So even for the ground state, first excited state, and so on and so forth. They are nodeless in the sense that if you take absolute value of any of these psi's, you don't get any nodes in any of these functions. Even not for the ground state or first excited state, there are no nodes. So they're kind of like odd. But on the positive side, this is not written here. You can get a very good intuition of this by doing WKB approximation for this upside down potential. And then you get this dashed and dotted curves for the wave functions. So for instance, for the ground state wave function, there is a dashed curve here, which is this thick black line, which is very close to the numerically calculated value. And the imaginary part is this dashed red line here, which is also very close to the imaginary part of the wave function. So you can sort of get a good intuition of what's going on by treating this problem using the WKB approximation. And not surprisingly, WKB gets better as you go to the higher order wave function. So first excited state and second excited state, you essentially can no longer tell with your naked eye which one is the WKB and which one is the numerically calculated solution. Okay, so the WKBs, these are analytic solutions. You can write them down. They sort of involve, there are some Airy functions or something like this that crop up, but nothing more fancy than that. The spectrum is likewise easy to calculate using this numerical technique. I show here the spectrum again for this inverted quartic oscillator as a function of the level number. And what you can see is these numerically calculated dots are sort of shown here in this blue, squares. And as a comparison, again, I've plotted the WKB result, which again is analytic. And this is this black line here. And you can see there's a very, very good agreement between WKB and these. So WKB for the upside down potential and the corresponding energy levels. Here I have sort of taken this and sort of extracted the difference between the energy levels and the WKB -1. So if they were perfect, then this difference would go to 0. And it turns out that if you look at the level 0, so the ground state, you're about 15% off. But sorry, about 8% off. And then if you sort of go to a higher levels, this difference sort of quickly approaches 0. So the fourth excited state, the WKB is about only 1% different from the numerically calculated value. Okay. So WKB works very well in giving an analytic understanding of what these wave functions and energy levels for the upside down potential are. Okay. You can do more. You can also calculate what's known as the spectral zeta function for these potentials. So you take an upside down potential -x⁴, and you can define the spectral zeta function. For those of you who have not seen this before, these are the sum over the inverse eigenvalues raised to some power alpha. That's why it's called the spectral zeta function, not the Riemann zeta function. It turns out that even though you don't know the energy levels for the upside down potential analytically, you can calculate the spectral function analytically. Okay, so zeta s of 1 is this function, gamma 5, gamma to the 5th power of 1/3 divided by 12 to the 1/3 over 4 pi squared. Yeah. It turns out that you can not only do this for the spectral zeta of 1, but there's a whole web of relations that you can derive using exact WKB methods. There's a very nice paper by CEO Kamada that sort of came out last August. They sort of goes through this and sort of derives relations, so some rules that, for instance, relate this zeta s of 1 to the 3rd power to zeta s of 2 and zeta s of 3. And you can use this to kind of like bootstrap your way up to sort of get analytic results for zeta s of higher powers. Okay. So again, I will stress that even though, so in this case, you don't need to sort of define anything. You're not sort of really have to deal with wave functions or energy levels or anything like that. All you do is look at the spectrum of the operator. You sort of look at spectral determinants, and you use this magic that sort of was written down by André Borsch in the sort of 80s to sort of really get analytic results for properties that have to do with the spectrum of this upside down potential. And the main point is that since these spectral functions come out to be finite, you can immediately draw the conclusion that the spectrum has to be bounded, because if it was not bounded, then these spectral functions would all be 0. And the fact that you have these results that are finite and these sum rules let you sort of put a mathematically rigorous statement saying that, oh yeah, the spectrum for this upside down potential has to be bounded because of exact WKB. Finally, sort of to give you a little bit more meat about what is going on here, let you give me another perspective on this negative coupling field theories, which has to do. Yes.
So this is just, but only for the massless case, right? Like it's purely
right. Yes, for the purely yeah, exactly. This potential that I've written down here. For the purely quartic potential, you can do this. You can also do it for a mass term, but the answer is not as nice. Okay, so it's extremely unwieldy and involves special functions.
Yeah, but still is a bounded spectrum.
It's still a bounded spectrum. Yes, that's right. Yes. You can, okay, maybe sort of going back, you can actually, it's possible to sort of do this isospectral construction not only for the quartic case, but with a mass term. And you find that you get a Hermitian Hamiltonian that's isospectral to the one with the mass term. So you know that it's bounded, but it's not analytically known. Okay, so now let me sort of give you maybe the most physical perspective here, which has to do with scattering. To set the stage, let me remind you that as a student, you were asked to calculate transmission and reflection coefficients of scattering problems, right? So you had this potential, like a box potential, and you had some incoming wave, and then you were asked to sort of calculate the amplitude of the wave that sort of would sort of go above the potential and then through this, and you had to sort of calculate how much of the sort of incoming amplitude was scattered and how much basically was absorbed and how much of it would sort of go and be reflected. So let's do this now, but for the case of an upside down potential. For an upside down potential, there has been quite a bit of construction with the idea that this scattering perspective is something that can be experimentally implemented. And to implement this experimentally, you typically want something that does not go to minus infinity, meaning that the hill sort of ends at some point and goes to some flat region, because experimentally you cannot sort of set up something that goes to minus infinity. Okay. So for this reason, people have considered potentials that are this upside down potential, so minus x to the p, but then cut it off at some specific position. Okay, so for instance, here there's a sketch here by paper by Michelin and company, where they sort of cut the potential at around position 2, and then it sort of becomes flat for positions that are sort of higher than this. And you have two parameters now, which is the power of the potential and the position at which you've basically cut it off. Okay. It turns out that you can look at the scattering problem for potentials like these. And here I show you from the same paper the reflection coefficient as a function of the incident energy for this cutoff potential. And what you find is the following thing. You find that you have to look at this sort of oscillating curve over here. The reflection rate is some number from most incident energy values. But there are special energy values, E0, E1, E2, and so on and so forth, where the reflection rate goes to 0, even for these cutoff potentials. Here there's a logarithmic plot, and you can sort of see these, right? There's E0 here, E1 there, E2 here, E3 there. So there's these special energy values where there's no reflection at all. There's perfect transmission. So again, for ordinary scattering on an upside down potential like this, and I'm taking the sort of not cut off version of this, if you send in the wave packet, it will typically scatter, and you will have both reflection and you will have a reflection coefficient that's non-zero. But there are special energy values for which the reflection coefficient is exactly 0. So these special values, which sort of sometimes go under reflectionless scattering, for these special values of energies are precisely the energy levels that you get by diagonalizing your upside down Hamiltonian. Okay, these are the spectral, these ENs that I showed you that sort of come out of the paper by Jones and Matteo, that come out of the numerical study by Bender and Böttcher, that come out of the numerical study of DWKB. So these are these energy values. So what you find is that for these special energy values, there are wave functions that are exact solutions of H psi E psi, and you have no scattering at all. So the interpretation of these is that you have 0 width resonances. Okay. All of you have at least heard at some point about resonances in quantum field theory, right? So basically, if you take I don't know, let's take the deuterium. Deuterium is a quantum mechanical system that has a bound state, but it also has a resonance. And it's actually a non-trivial calculation to figure out whether the ground state is the triplet or the singlet state. But it turns out that you have both the triplet and the singlet state, and one of them is the bound state, so basically has an energy less than 0, but there's also the resonance, and you sort of see the resonance, for instance, by scattering onto deuterium. Okay, many systems in quantum mechanics have this property. So what we find is that for these special upside-down potentials, there is a whole range of resonances with energy E0, E1, E2, and so on and so forth that characterize the spectrum of the Hamiltonian for these systems. Let me sort of, again, repeat this. So for the upside-down potential, negative coupling, there's no stable classical bound state. However, you find quantum mechanically there's a set of narrow resonances at these energy levels, E0, E1, E2, which are all bigger than 0. Because you have these resonances, you can set up a partition function the usual way, so the sum over the Boltzmann rate with these energy levels. And this partition function is perfectly well behaved, right? You have your energy levels, you have your resonances, you sum up them with a Boltzmann factor, you get a partition function. This is basically as standard as it gets. This partition function is well behaved because all of these energies are real and positive. There's nothing funny going on with this quantum mechanical system, even though classically it makes no sense. And because this partition function is well behaved, the theory is perfectly unitary. You can look at amplitudes. The sort of time evolution is well defined. So the system behaves perfectly well defined from a quantum mechanical perspective. But of course, quantum mechanically, because classically, you don't have access to these resonances because classically you don't see any of the resonances. So that's why classically you don't have any understanding of what's going on in the system. But quantum mechanically, because of the presence of these resonances, you sort of understand that, okay, I shouldn't think of this as kind of like a bound state problem at all. I should think of it as a terms of, are there any resonances in the system, and define essentially my physics in terms of these narrow resonances that I have for the system. Okay. Questions up to this point?
When you say no classical interpretation, do you mean just directly classical mechanics, or because you gave examples on WKBN, which is related to some classical underlying classical mechanics? Well,
yes. If you say that WKB is classical, then yes, there's an understanding from classical from WKB. However, I will caution that the turning points for these potential are purely imaginary. Okay, so you tell me what that means classically.
Okay, but
yeah.
They have meaning in the semi-classical.
Right. Yes.
Okay.
But classically, I mean actually classical, meaning no H bars at all.
Okay.
Yeah. Okay. Fine. So I spent quite a little bit of time trying to sort of give you different perspectives on negative coupling quantum mechanics. Now let me tell you a little bit about negative coupling field theory, which is maybe the main subject of interest for you. It turns out you can do many things that have to do with negative coupling field theories in 1+1 and 2+1 dimension. It's interesting. There's lots of interesting physics that comes out of this. I am preparing a preprint that will have a title somewhere around the lines of Curious Set of Self-Dualities soon. But in the interest of time, I will concentrate on the case of 3+1 dimensions for the remainder of this talk. To set up the stage, I will consider a theory that has scalars in 4 dimensions, but it's not just one component scalars, it is the ON model that I want to talk about. And one of the reasons to do this is that for quantum mechanics, I had all these other non-perturbative techniques that I could use to study, right? I had WKB, I had direct diagonalization of Hamiltonians, I could use spectral functions. For field theory, many of these tools are not existent or extremely hard to sort of implement. So I want to have a different way to solve the theory that has nothing to do with a weak coupling expansion. That's important. And to do this, I want to have an expansion parameter that's small, and I take this to be 1 over the number of components of my scalar fields. Okay, so I'm considering a scalar field phi vector that has n components, phi1 to phi n, and I will solve the theory in powers of 1 over n, where n is the number of components. Otherwise, this is a perfectly canonical setup. This is the Euclidean partition, the Euclidean action for this theory, and then I have a partition function defined the usual way. Yes, so that's what I just said. So for those of you who have not dealt with these large N techniques, I'm afraid that you will only have to believe me about what it is that I'm doing. I wrote down, well, I gave a multi-hour lecture course on large N techniques 2 years ago, and I've written up lecture notes that maybe will make it into a book somewhere down the line. You can look at these lecture notes on the archive. They're given here, and this has information not only about scalar field theories, but also about fermionic field theories. In particular, it has applications to neutron star physics, so-called atom physics, and other aspects. Okay, so let's jump in. The main trick to solve these OM models in 4 dimensions, or actually in all dimensions, is to use a mathematical identity. It is the identity that e to the minus something x to the 4 can be written as an integral over an auxiliary field zeta and a quadratic or Gaussian variable. Okay, so if you stare at this a little bit, you realize, okay, here I'm integrating over some variable zeta. The action here is quadratic. I have to complete the square in zeta, and that will give me a quartic term as an outcome. Okay, so this is mathematically non-disputable, and I will use this to rewrite the quartic term in my action in terms of a path integral over this auxiliary field where only quadratic terms appear in the action and this mixed term here. Okay. So once you do this, you only have quadratic terms in the action. Quadratic terms in the action are Gaussian integrals. So I can directly do the path integral over phi vector because it only appears quadratically in the action. And I get a different description of the same theory in terms of this auxiliary variable zeta. So this is the prescription, and what you find is that, yes, there is the determinant of the operator of phi, so you can recognize the minus partial derivative phi squared here. You can see the 2i zeta, which is coming from this over here. And then you have the term that we use to first of all introduce or get rid of this quartic term. So this alternative description of the same partition function of the theory in terms of a different variable zeta is mathematically exact. Okay. The main point is that in this description, you can see that the action is proportional to n, the number of components. So if I take n to be large, I can use a saddle point method to get exact results in a 1 over n expansion. This is not manifest in the original description, which is why I wanted to do this rewriting. Okay. Once you have it, then you have the n's over here, and you can use the saddle point expansion of integrals of these forms. I've written it down again here. An integral over x of e to the minus n times some function f of x is e to the minus n times the function evaluated at some saddle x naught, and then Gaussian corrections and other corrections that are 1 over n suppressed. Okay. All of you probably have seen this many times in a mathematical physics course. Okay. What is this x naught? It's the saddle point of the function, and if we go to our function here, the path integral for the scalar field theory or the OM model, you find that the end result of this exercise is that the logarithm of the partition function is given as n times the volume, which I write as beta v. Beta is the inverse temperature, v is the 3 volume, times a function p of m, which is essentially this function here. We have changed notation from I zeta to p. What you find is that this function p is essentially the free pressure for a massive particle m plus the term m over 16 lambda. Again, this is probably very fast if you have not gone through this exercise, but if you sort of have 10 minutes, you can sort of go through this. It's really sort of undergraduate mathematics to sort of get to this point. This M here is the location of the saddle, and the saddle point condition is such that the derivative of this function P vanishes. Okay. Okay. If you
Where did the temperature come from?
So I solved this theory on a Euclidean circle. Sorry, I didn't say anything about that. So I sort of only wrote down that my Euclidean action is an integral of x. I didn't tell you that my Euclidean time tau is compactified on a Euclidean circle with length beta. So I think for most of what I'm talking about, I will actually sort of have the temperature set to 0. So it's actually not relevant, but the point is you can do it without any extra effort, so I keep it usually.
And so it's also still, this is in 4 dimensions.
Yes. Yes, I'm in 4 dimension. You can do this trick for any dimension. And in fact, you can check that the method works by comparing, for instance, to bootstrap results for critical exponents in 3 dimensions. It sort of works very nicely. But what I want to really apply to is 4 dimensions. Okay, good. So fine, you do a calculation. You basically have to believe me that I did my math right. But at the end of the day, you find that this partition function can be written in terms of this thing here. And this function P of M is a physical concept. You can use your long-lost knowledge about thermodynamics to realize that this P of M is the pressure, or minus the free energy density of this theory. Okay, so that's the physical sort of interpretation that I want you to have in mind. That's what I'm calculating. And if you do this in 4 dimensions, you find that you have a pressure function that looks like this. There's an m to the 4 over 16 lambda. There is a divergence because, in 4 dimensions, we often have divergences. In dimensional regularization, there's a 1 over epsilon that appears. And there is the ms bar randomization parameter mu bar that appears, some exponential e, and another logarithm of m squared. Okay. Again, this is perfectly standard. You just sort of look up Peskin and Schroeder and look up what the free energy of massive scalar is, and that is basically what you find here. Okay, if you look at this function here, you realize that, okay, because there's a divergence, we have to do renormalization. And you find that, oh, wait a moment, this is easy to do. There's an m to the 4 that has the divergence. There's an m to the 4 that has the bare coupling constant. Well, I know what to do. We'll write down a renormalization that says that 1 over the bare coupling constant is 1 over the renormalized coupling constant as a function of mu bar minus the divergence in the ms bar scheme. Okay. Of course, if you do this, then in ms bar you get immediately some running coupling out of this construction. The exact running coupling at large n is given by this function here. It's 4 pi squared over the logarithm of lambda ms bar squared divided by mu bar squared. Again, no discussion, right? You just turn the crank. It's quantum field theory at its easiest. Okay. The point here is that because we're not doing perturbation theory, we're doing this 1 over n expansion. This result is large n exact. Okay. There are 1 over n corrections, but to leading order in large n, that's the result. Period. Let's look at this function, the lambda r of n. Okay. That's what it looks like, and you can realize why it looks like that. If we go back. This function here for small values of mu bar, this ratio is larger than 1. The logarithm of something larger than 1 is positive, so you get something that's positive. But if we increase mu bar, this ratio becomes smaller and smaller. So we will divide by something that gets smaller and smaller, so it becomes larger. So that's why this coupling constant rises. At one particular point, namely when mu bar is exactly equal to lambda ms bar, you have a logarithm of 1 that is 0. So dividing by 0, so this diverges. And then it becomes smaller than 0, so you sort of come back at minus infinity. And at extremely large values of mu bar, this ratio is smaller than 1. The logarithm is negative. So this function again sort of rises, but it rises towards 0. So that's this behavior of this function. Okay. And you know this function, right? I mean, normally in perturbative quantum field theory, you sort of calculated this function here at very small values of the coupling, because you said that, oh, I wanted to do small coupling perturbation theory, the beta function is positive, yada, yada, yada. You also heard that this theory is not defined as a continuum theory because the beta function is positive. This theory needs to be treated as a cutoff theory, and so on and so forth. I'll talk about what that means. But if you don't do any of that, you just sort of calculate in a well-defined 1-over-n expansion, this is the result that you get. I will tell you, for those of you who maybe have ventured into cold atom physics, look up the scattering length as a function of the magnetic field where you have a system undergoing a Feshbach resonance. You'll see something interesting, okay? Why is this important? I'm trying to sort of wrap up here. First of all, there's this notion about quantum triviality, meaning that this scalar field theory does not have an interacting interpretation in the continuum limit. This is a big thing, okay? So there is a proof in mathematics by Michael Eisenman and Hugo de Menil-Coppin. In their words, they sort of essentially prove that there is no four-dimensional continuum description of scalar field theory that is interacting. And why this is a big thing, I should sort of point out that so these are these two gentlemen, Michael Eisenman and Hugo de Menil-Coppin, and Hugo de Menil-Coppin got the Fields Medal for this in 2022. Okay, so it's a big thing. If you look at the proofs, in particular what Mike Eisenman has sort of pointed out many years ago, you'll find interesting statements such as this one. Considerations of asymptotic freedom in phi-4 for dimensions 4 or greater have led to a suggestion that one could try to make sense of a theory with negative coupling, in which case the probabilistic interpretation suffers, which is just code for saying that their mathematical proof does not apply. Okay, it's a loophole in their proof. Their proof is only valid for positive coupling field theories, and this is something that Mike Eisenman confirms by email if you ask him. So if you look at our coupling, you find that, whoops, look at what it's doing. At high energies, it's actually negative, okay? It's an upside down potential. So this theory, this calculation, which doesn't know anything about sort of quantum reality or any of these things, automatically tells you that, oh, I am exploiting a loophole in this mathematical proof, and I'm perfectly fine being an interacting quantum field theory in the continuum because I just don't do what they sort of assumed in their proofs. Okay. Another reason why this is important. You've seen plots like this before. This is the QCD coupling constant lambda alpha s as a function of the energy scale. This is a famous plot from CERN where you compare the QCD next to leading order perturbative calculation, this line here, to some experimental data from lab. And you'll find that, yes, the coupling constant decreases as a function of the energy scale. Okay? This is known in the physics literature as having a negative beta function, while clearly the beta function decreases. And this has an important consequence, namely that QCD is a theory that has asymptotic freedom, meaning that extremely large energies, the coupling is essentially zero, so quarks and gluons are essentially free. That's what I just said. This is an important thing because the gentlemen who were involved in these actually got the Nobel Prize in Physics in 2004, David Gross, David Pollicer, and Frank Wilczek. And David Gross also sort of wrote the paper together with Sidney Coleman around the same time, saying that this is not a coincidence that QCD has this property because all known examples of asymptotically free theories involve non-abelian gauge fields. We show that this is no coincidence. No renormalizable field theory without non-abelian gauge fields can be asymptotically free. That's their statement. Okay. Let's look at our plot again. Let's look at what happens at high energy. The coupling constant is negative, but it rises because the beta function is positive. And if you go to very high values of the energy scale, you find that the coupling constant approaches zero from below. What does that mean? It means that scalars are asymptotically free if you sort of don't interpret them in terms of classical physics. This sort of fact that it's negative but approaching zero from below exploits the loopholes in the proof by Coleman and Gross, And it's the same loophole that the theory exploited for avoiding quantum triviality. Okay, I'm out of time. Let me just summarize. My main message is that I want you to stop trusting classical intuition. Just don't do it. Quantum mechanics does not conform to classical intuition. Don't try to make it, okay? On the other hand, mathematics is an extremely good guide for quantum systems. It has been shown over and over and over again that mathematically we can unlock things that do not conform to our classical intuition, but do describe experiments. Okay, so trust the math, don't trust the classical intuition. Also, because of history, I think there are what I would call mental roadblocks, in particular for quantum field theory, erected by our more senior colleagues. Okay, I want you to try to ignore them. Okay, this is hard to do because some of you might want to get a job, but nevertheless, think of this. What I want you to do is calculate observables and check whether whatever they said could not be done is actually true. Okay. Finally, I will point out that because of these quantum triviality proofs, many QFT textbooks are essentially built on classical intuition, right? You start with this sort of setup that you have this classical ground state with a massive particle, and you start expanding around this imperturbation theory. If what I'm saying is true, I think there's an alternative description that does not rely on classical system. Basically, what I'm saying is that there are quantum field theories that do not have a classical description. And these might be important. They might be important for many sort of examples. The electroweak sector in high energy physics is one case. QCD is another case. Maybe quantum gravity is another case. So there are potential sort of a lot of examples where this could happen. And I think these negative coupling field theories are a very good road into these kind of non-classically sort of existing quantum field theories. I'm out of time. Thank you very much for your interest. And I hope I didn't talk your ears off. I'm still here if you have questions. And otherwise, thank you for listening and hope to see you again.
Thank you very much, Bob. Are there any questions?
How much of that you just told us in the second half depends on the fact that you put it on torus or having a beta? What happens if you put it on RD, R4, I guess, or something?
Yes, so it does not. So essentially, all of the results that I've shown you are calculated for R4.
Okay.
I have results obviously for torus as well, but I didn't talk about that at all. So all the results that I've shown in this talk are for R4. We also have results for STs if you're interested in that. Yeah, so that essentially the main sort of talking points are the same. Okay.
Okay.
What would happen if you have multiple different interactions with different couplings? Could you still, or should you still assume they could be negative and just start from that point?
That is an excellent question. I don't think I have an answer for that. I try to sort of do simple things which only involve one coupling parameter. If you have multiple dimensions in your coupling parameter space, I think that potentially can have very rich sort of phase diagrams where you have some corners where the field theory does make sense. Quantum mechanically, you may have systems where some parameter space values don't make sense quantum mechanically. I think it's large. I think it's unexplored for the most part. But I think you and your collaborators have been sort of interested in tensor networks where you have more than one coupling parameters, and so I think this is a good example of a theory to sort of look at in this context. And I think you're the expert to tell us what happens in these systems.
Back when you were talking about quantum mechanics and you had the spectral zeta function,
Yes.
Is there like any sort of relationship between the spectral zeta function for the negative coupling theory and the positive coupling? Like, do they have like the same relations or something? Because
Yes.
Okay.
There is relations. The relations are So I have a paper where I think I write down at least a relation for zeta s of 1 between the positive and the negative coupling field theory. I think the difference is just a factor of 1/2, if I remember correctly. You can show what arises. There are similar relations known for zeta f of 2 and 3 using essentially C. Okamoto's result for these sort of sum rules in both of the positive and negative coupling field theory. For higher values of the argument of zeta, I think the relation is not known. If you were to figure out what the relation is, I think this would be a big step towards sort of unraveling some of these issues. I should say the spectrum of the Hamiltonian is not known analytically either for the positive coupling x to the 4 nor for the negative coupling x to the 4 theory. But because of this fact that you have these analytic results for the zeta functions and these sum rules, many people believe that such analytically known spectrum is calculable if you just find the right trick. And it's an open problem in mathematical physics to do this, and you're guaranteed to receive a prize if you are able to sort of find the corresponding analytic expressions, either for the positive or negative coupling.
Cool. Okay, thank you.
So for the negative coupling, does it have any bearing to universality? Like, do we get different critical exponents if we go to a negative coupling?
So you're talking about sort of critical exponents for sort of quantum field theory in, for instance, 3 dimensions, something like this.
Right. I mean, maybe even 4 dimensions.
Yes. I don't know. My suspicion would be that. So in 4 dimensions. Okay, maybe I should have said this. Okay, let's back up. I could easily imagine that critical exponents for negative coupling field theory in 2 and 3 dimensions are different. So I think this work has just not been done. I think it's an interesting question to sort of do this. I don't know. But for 4 dimensions, I want to point out that we don't actually study the negative coupling field theory from the outset, right? So we write this positive coupling constant in the Lagrangian, and it just happens that after renormalization, the coupling constant has both branches. It has a branch where it's positive and it has a branch where it's negative. So the 4-dimensional theory, you don't have lambda as a parameter. You don't get to choose lambda. It gets sort of automatically generated via radiative corrections. You can't do anything about it. It has both a positive coupling regime at small values of the energy scale and a negative coupling regime at the high values of the energy scale. And really sort of this points towards the possibility that 4-dimensional scalar field theory has 2 phases. Okay, one phase that's characterized by the low energy, and one phase that's characterized by high energy. And this is really, I would say, potentially similar to what is happening in QCD. Where we sort of
confinement in 5.4.
Yes, except that in 5.4, we don't think that it has to do with confinement. It probably is some other sort of order parameter that appears, but it could have 2 phases, similar to the fact that QCD has 2 phases. And I'm not just making this up. So if you again think of, well, maybe you don't know about this. In cold atom physics, when you sort of take rubidium atoms and you sort of apply a magnetic field, you have this fact that you have a Feshbach resonance that is S-wave scattering length goes from positive to negative. And people know that nothing bad happens when the S-wave scattering length diverges. This is just the unitarity regime in cold atom physics. However, people do know that for the 2 sides of the coupling or the scattering length, you get 2 different phases of the theory. One is the BEC phase, where you form a Bose-Einstein condensate, and the other one is the BCS phase, where you form Cooper pairs. And there's a crossover between these 2. So it could easily be that what we're seeing here in 5.4 theory is just that, right? So you have one regime where you have a Bose-Einstein condensate, one where you form the equivalent of Cooper pairs, except that they're not charged. And the analogy is actually such that you can actually go back to my calculation and find that I've introduced this auxiliary field here. If you look at my lecture notes, if you do this for fermionic field theories, you can interpret this to be the Cooper pair field. Okay, it just comes out of the calculation. So there's, I would say, strong evidence that there is a relation, or at least a physical interpretation, that says that scalar 5-4 theory in 4 dimensions has similar characteristics as this BC-BCS transition in core atom physics across the Feshbach resonance.
And the order parameter there is the bilocal field, right? Like
it's the same here. So here the theta here is also the bilocal field.
yeah. Another question related, I mean, if I understand correctly, so even in the negative coupling regime, this is unitary.
Yes.
Right? So most probably we can see that through one of these I always forget C or F here. What can
I'm not sure. So, but yes, you can calculate the corresponding F number for this theory, and it's perfectly well defined. It's monotonic. It does what it should do.
Okay. In quantum mechanics, basically there's this spectral theorem backs up the complexification process, this choosing the complex boundary conditions.
Yes.
Do you have something similar in the field theory context for PT symmetric, for example, 5-4 theory?
Yes, in the sense that if you sort of define the field theory, okay, so there's different boundary conditions whether you want to approach the problem from the path integral perspective or the Hamiltonian perspective. The boundary conditions are different. However, you can look at the path integral perspective, and there it turns out that the boundary conditions that you need for these negative coupling field theories can be chosen identical, whether it's quantum mechanics or quantum field theory. It can always sort of be this contour that is somewhere in the Stokes wedges. And the Stokes wedges for 5-4 theory, you have some opening angle, and the 45 degree is somewhere in the middle of that. And it turns out you can do this for quantum mechanics. You can use the same prescription for quantum field theory, and there's no difference. From the Hamiltonian perspective, I think there is a difference, but I've not tried to sort of really implement that for, well, we've tried, but it's not quite as simple to sort of do the Hamiltonian formulation of quantum field theory in more than one dimension using this sort of contour deformation.
But is it the same prescription that shows that this is a reflectionless scattering process? Is it the same logic?
No. So at least I wouldn't know how to use that directly. So I think the interpretation for quantum field theory is still being developed. So I don't think there's any simple interpretation that is analogous to these reflectionless scattering problems in quantum mechanics. Yeah.
Thank you.
Any more questions?
just one question about the phase, maybe a very naive question. Can you bring the phase diagram or the RG flow for?
Let me see. This one?
This one. Yeah, I mean,
okay.
Naively, like because we are in a massless regime here, we don't have a quartic coupling. Doesn't it seem like below zero we have some correlation length, and above zero, like we have zero correlation length because it's massless, something like that. So I'm just wondering, like, if there's a BKT like transition happening as well.
So what I sort of showed you here is just the running coupling of There is, of course, also you can play the same game with a mass parameter, and there's a corresponding plot for the mass parameter as well. And then depending on these ratios, you can have more interesting phase diagrams. It turns out that the existence of a mass parameter doesn't change the running coupling at all, right? And the coupling gets renormalized, and that's the answer for the coupling. The mass gets renormalized, and it has its running coupling. But the phase diagram, yes, gets more interesting. And indeed, there are transitions that you can sort of find when you change a mass parameter from zero, and yeah, you'll get different phases. Again, I think my suspicion is that much of this can be sort of understood in terms of transitions having to do with broken symmetry versus restored symmetry transitions. At least that's the case in lower dimensions. And again, I'm trying to write up a preprint where I sort of show how that works out in 2 and 3 dimensions specifically, and also treat the 4-dimensional case. But basically the upshot is that canonically you find that depending on your Baire parameters, mass and coupling constant, you will have phases where the expectation value of your field phi is 0, so this is the symmetric phase, and others where the expectation value of phi is non-zero, so you have an unbroken phase. And then the transition between the two of them is something that I think would be harder to calculate using any of these techniques, but the existence of these two phases, I think, is generic and actually matches what you get from lattice calculations in 2 and 3 dimensions.
If there are no more questions, let's thank Paul again. Thank you very